Okay, so we have two reactions that we're gonna show today in the virtual lab. Both are reactions that we would do, and the first is going to be thermite, and the second is going to be making polyurethane foam. So these are very different in the nature of the reaction and what they're used for. Both have very much industrial purposes. So we'll go over each, where the thermite is a good example of a reaction that releases lots of energy, and the polyurethane foam is a really good example of a polymer, a very ubiquitous polymer that we see a lot of in industrial applications. So we will start off with the thermite. So the thermite reaction. Um, so thermite is a compound that was historically used to, and is actually today still used for welding railroad tracks together. So has a very long use. There are many different. Thermite is a generic name for the process of taking a metal and a oxide of iron oxide or rust, adding them together to create aluminum oxide or the metal oxide. So, for example, what we're going to do today is two aluminum. Aluminum is just cheaper and easier to find, but you can use other types of metals in replacement. And again, rust, Fe2O3. This is rust. And this is not a block of aluminum. This is like a very fine powder. Because what we want to do is we're going to be mixing, and rust is also going to be a powder. And you'll be able to see this. Um, so we have the aluminum and the rust will be mixed together, and they are going to create two iron solid plus aluminum oxide, Al2O3. And the amount of thermal energy released is 850 kilojoules per mole. Now that is insane. That is a lot, and so we'll see that. This releases a huge amount of thermal energy. And that's why it can be used for things like welding railroad tracks together. So the let's see, the part of the reason why, I guess we can talk about this. So we have, we'll link this back to what we talked about in lecture. If we think about our energy diagram, what we're going to have here is we're going to have, this is energy. We're going to have our aluminum and our iron. And down here, we'll have our iron and our oxygen. I'll put the coefficients here. And what we're saying here is that this delta E is 850 kilojoules per mole. So that is the difference between the energy of the reactants, aluminum and iron oxide, and the products. Now, just like we saw, there's some activation energy that we have to overcome. And so if I just have aluminum and iron oxide together, they will not react. We need to add a catalyst. In this case, we're going to ignite with a sparkler. You can use other types of ignition sources, but sparklers tend to be safest and work best. And so that's an idea. Now the reason why, so if you look at this, aluminum and iron oxide don't particularly look that different than iron and, oh, this should be a, I forgot an L down here, and aluminum oxide. So what's the difference? And really it comes down to the difference between iron oxide and aluminum oxide. So both of these, we have iron surrounded by aluminum. And in this particular arrangement, oh, sorry, that's not right. We have iron oxide, so we have O, 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 O. Now the oxygens are -2, or 2 minus, 2 minus, 2 minus, and the iron is +3. And so these are all going to be interacting because positive and negative charges attract each other. And so the size of the iron is much larger than the size of the aluminum. So the aluminum, when it interacts, so we have the aluminum and the oxygen, 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 oxygen. Now in this case, the aluminum is also +3. These are still 2 minus. But you'll see that these are actually much closer. And because the closer the charges get together, the stronger their interactions. And so because the oxygen can get closer to the aluminum, we see this major energy release. So again, more interactions, strong interactions provide lower energy, and that additional energy is released in the form of thermal energy. So that's the main reason why, even though they look very similar, they have different properties. Specifically, the attraction strength of the aluminum and oxygen are much greater because the oxygens can get much closer to the aluminum, increasing those interaction strength. So that's thermite. And so that's a little overview of the reaction. So we're going to be pouring aluminum and rust together. Okay. And so the second reaction that we'll be doing is polyurethane. So polyurethane is, polyurethane is a generic, unlike some of the other polymers that only have kind of one formula. Polyurethane is a class of molecules that uses a specific linker, and you can change up the different functionalities on either side of this linker. And so the linker is urethane. And so we have this linker of a carbon double bond O, and then we have a nitrogen with a hydrogen and an O here. And so this is the, well, I'm actually not going to put that because that's the wrong notation. So this here is your urethane linker. Now, what gets attached onto either side of the urethane can be different. So this is unlike other where we say polypropylene. The propylene molecule is just repeated over and over and over. Now this isn't the case. This linker is used over and over and over with many different types of groups that can be attached on. So let me give you an example of one that we have. The actual experiment we do today is proprietary. They don't actually tell us what it is, but I can give you an example of one. So we've got a benzene with a nitrogen, double bond carbon, double bond oxygen. And then on this side, we've got carbon. And then that's attached to another benzene. And then that's attached to a nitrogen, double bond carbon, double bond oxygen. Now this is an important part of, you'll see most of the polymer units that we make, they actually have, see how this and this are mirror images each other? That's really important. It's kind of like you have two sticky sides, you have two reactive sides. The only way you can self-propagate through for long chains is if you have two sides that both have the same kind of reactive component. And you'll notice that the other molecule we have is an alcohol. So in the same way, we have an OH group on either side, and then just hydrogens. Okay, so again, we have those kind of carbon OH on either side, and that's going to be the linker. And so what these are going to form are we'll do this kind of sub, so it's going to form one link here. It takes a sec to draw this. So we have this middle component. We have two of them, so another one. We have a nitrogen, hydrogen, carbon, oxygen, carbon, and then here's our alcohol. And actually, I need to get rid of that H because we will link from that. So it goes like this. And what you do is you say that this unit repeats over and over and over. So this, like most polymers, we would say the monomer is what's in the brackets. Now, in this case, we don't call this the urethane molecule. It's not polyurethane. This is a type of polyurethane, but it has this urethane linker, so this NCO. So if I do this in purple, so if we look at this and we come down here, we can see this is our urethane linker that has this molecule from here and this molecule from here. And so that's an example of a type of polyurethane. You can have different types. So it maintains this type of polymeric structure, but it's somewhat unique in that it's a general class of these urethane linkers, but you can put a lot of different things on, and that gives polyurethanes many different types of properties. To be soft, to be hard, foam, depending on what you put in. So that being said, that's a little bit. I think that's all we're going to go through. There's a lot more to this reaction, but we're not going to worry about that. So that is the two reactions. So urethane, polyurethane, and thermite. Again, very different reactions, but we're going to see both of those in our lab today.